Okay, good morning everyone. So we were talking about orthonormal basis for a Hilbert space. So today I'll prove this theorem. That a Hilbert space has a countable orthonormal basis if and only if it is separable. So separable means that it has a countable dense subset, and this is equivalent to saying that it has a countable orthonormal basis. So to prove this, first of all, suppose it has countable orthonormal basis, then we have to find a countable dense subset. So suppose H has a countable orthonormal basis, let's say En. Then we have to find a countable dense subset. So what we know is that if we look at the set of all finite linear combinations of orthonormal basis, then that is dense in H. Right? So we will use that result. We know that the set of all finite linear combinations of En this is dense in H. So from here it is easy to see how to get a countable dense subset. So you look at the a linear combination where the scalars are rational. So let S be the set of all finite linear combinations of En with rational coefficients. So if the field is real, then we look at summation of this alpha I ei, where alpha I are rational, and for complex, we look at the scalars such that real part and imaginary part are rational, right? So this means that for complex, real and imaginary parts of the coefficients to be rational. So then clearly this is a countable set, and also because the set of all finite linear combination is dense, so, and rational is dense in R, or this thing is dense in C. So therefore, we'll get that this is a countable dense subset. So then S is a countable dense subset. Now, conversely, suppose the space is separable, that means that it has a countable dense subset, then we want to show that there is a countable orthonormal basis. So, so we'll show that if there is any like orthonormal set, then it has to be a countable. That will prove that it cannot have uncountable orthonormal basis. So for the converse, so we let xn in n be a countable dense subset of H. Now let us take any orthonormal set. So let EI, I in I be any orthonormal set. So we will show that this I is countable, and that will imply that it it has a countable orthonormal basis. So so what we know is that if we have an orthonormal set, then if I look at EI and EJ, then the distance between EI EJ is equal to square root of 2 for every I not equal to j. So if we take suppose balls of radius less than this distance between EI and EJ, so less than half of that distance, then uh, we know that each of that ball will contain at least one point from this countable dense subset, right? So for every I, we get a point from this countable dense subset, and these balls are disjoint. So therefore, if this set is uncountable, then we will get uncountably many points in this dense subset. But this is assumed to be countable. So that will be a contradiction, right? So then norm of ei minus ej, this is equal to root 2 for all I not equal to j. So if we take so therefore the balls of radius let's say bei comma root 2 by 2 for I in I, these are pairwise disjoint. Also, since this is dense, each of these balls must contain a point from this set Xn. So this will imply that this I is countable. Right, because in for every I we get, so we will get a map from this indexing set I to natural number, and that map uh, is one map, right? Because if we take two different I's, then we cannot get same xn, right? Because these are disjoint. So therefore we get one map from I to n, and that implies that I must be countable. So this proves that Sorry, there was a connectivity problem. So yeah, so this proves that H has a countable orthonormal basis. Okay, next let me prove that every Hilbert space is isometrically isomorphic to L2 space. So this theorem is every Hilbert space is isometrically isomorphic L2 of gamma for some gamma. And if we take a separable Hilbert space, then it is isomorphic to the L2 space, which is L2 of n. So let's prove this. So we have to figure out what this set gamma should be. So this gamma will be the indexing set for an orthonormal basis. So suppose we have any Hilbert space. And suppose we take an orthonormal basis for this. So, and let let's call this as EI, I in gamma be an orthonormal basis. So this set gamma can be uncountable also. For separable Hilbert space, this gamma will be countable. Otherwise, it can be uncountable. So we will show that this H is uh, isometrically isomorphic to L2 of gamma. So what we know is that since this is an orthonormal basis, in the last class we showed that we have the Parseval's identity, which says that x can be written as uh, let me show that. Yeah, so we proved that these statements are equivalent. So if we have any complete orthonormal set, then we have this Parseval identity, which says that norm x square is equal to summation of this. And also we have that this x can be written as summation of x inner product ei times ei for I in I. So we get this. So then we know that for any x in H, x can be written as summation x dot Ei times Ei for I in gamma. Maybe instead of gamma, I can write capital I. So we have used capital I before. So x is equal to summation x Ei and norm of x square is equal to summation of mod x dot Ei square. So we know that this means if this set I is uncountable, then x dot Ei is non-zero only for countable set. So therefore, this summation will be countable sum over the set where x dot Ei is non-zero. And similarly here, we have only countable sum. So we have this. So now we have a map from H to L2 of this I. So, so what is that map? So for any x, we have these scalars x dot Ei. So, so let's define this. Define x hat from I to f by x hat of I is equal to x dot Ei. So for any x in H, we are defining this map. For x belonging to H, x hat is a map from I to the field of scalars given by this. So then we know that this x hat belongs to then x hat belongs to L2 of I. Why? Because we know that summation of mod of this square, that is finite. This is by Parseval identity. Summation of mod x hat I square. This is norm x square, which is finite. So for every x, I have defined x hat belonging to L2 of I. So now this map let phi from H to L2 of I be phi of x is equal to x hat. So then this phi is linear, because if you take say x plus y, then uh, x plus y hat of I is equal to x plus y dot Ei. So that is the x dot Ei plus y dot Ei, which is x hat I plus y at I. And similarly for scalar multiple, you will get this. So phi is linear. Also, phi is an isometry. So that follows by again this Parseval's identity, because the norm of phi x square is norm of x hat square, which is this summation, and that is the same as norm x square. So therefore norm of phi x is equal to norm of x. So this is an isometry, and this is also on to because if we take anything in L2 of I, then uh, you consider this summation of alpha I ei. So that will be an element of H, and therefore we get that this map phi is onto. So this will show that H is isometrically isomorphic to L2 of I. So if we understand what is this Hilbert space L2I, then we know all the Hilbert space, because any Hilbert space is isomorphic to this. And as a corollary, if we have any separable Hilbert space, then we know that it has a countable orthonormal basis, and therefore the Hilbert space will be isomorphic to L2 of n, which is same as L2. So corollary, every separable Hilbert space is isometrically isomorphic to L2 of 2L2, which is L2n. So this is because the if it is separable Hilbert space, then it has a countable orthonormal basis, which is separable. Then it has a countable orthonormal basis. En and Mn. So therefore, this H is isometrically isomorphic to L2 of. And if it is finite dimensional, then it will be isomorphic to L2 of 1 to up to n. So that means that the Euclidean space, finite dimensional Euclidean space. Okay, so next we will discuss about compact operators. Now we'll start a new topic. So let us define what is a compact operator between two Banach spaces. So let x and y be Banach spaces. So operator T belonging to Bxy is said to be a compact operator if T of B is relatively compact. So that means that is the closure of TB is compact. So this T of B is a subset of Y. So in Y, that the TB closure is compact, where B we are taking as the unit ball of X. So compact in Y, where B is the closed unit ball of X. So remember that a linear operator is called is bounded if T of B is bounded for the unit ball. Right? Here we are saying that T of B closure is compact. So equivalently, when T of B closure, this will be a closed subset, and for it to be compact, we require that it is totally bounded. So equivalently, maybe I'll write remark. T is compact if and only if T of B is totally bounded. Because we are assuming Banach space, so it is complete. So if we have a complete and totally bounded, that implies compact in metric space. So this will follow. And also we can use the sequence. So T is compact if and only if for every bounded sequence, there is a convergent subsequence of T of Xn. So for every bounded sequence Xn in X, Txn has a convergent subsequence. Okay, so this is the definition of compact operator. And let us use notation. We will use B0xy. This denotes the set of all compact operators from X to Y. And if we write B0 of X, that will be set of all compact operators on X. Also, let us define finite rank operator. Listen.
So can you explain those remarks again, sir?
Yeah. So the first one. So okay. So what do you know about a compact subset in a metric space? Do you know any equivalent criteria for compactness?
Yes, sir. Sequentially or limit compact.
Right. So one is if it is this sequentially compact, then it is compact, right? So what is that? That means that every sequence has a convergent subsequence in a compact set, right? Is it
Yes, sir.
okay? So that is what the second remark is, that we are saying that T is compact. Suppose T is compact. What does that mean? That means that if I take, yeah. So first of all, let me say this, that here in the definition I am saying that compactness means that the image of unit ball, its closure is compact in Y, right? Now, because this is a linear map, this also implies that the image of any bounded set, suppose I take instead of B any bounded subset of X, then its image is also relatively compact in Y, right?
Yes, sir.
So now if I take any bounded sequence Xn, then what we know is that T of Xn, if I look at the image T of Xn, its closure is compact, right? So that will mean that this sequence must have a convergent subsequence, right? Because T of Xn belongs to a compact set. Is it okay?
Yes, sir. And first one.
And, and conversely also. And the first one is that one other equivalent criteria of compactness is that a subset in a metric space is compact if and only if it is complete and totally bounded, right? what is the meaning of totally bounded? That for any epsilon positive, we can find finitely many epsilon balls whose union contains this set, right? So, oh, so this again follows because we know that T of B closer is compact. So T of B closer will be totally bounded, and T of B is a subset of that. So that is again totally bounded. And conversely, if T of B is totally bounded, then its closure is also totally bounded, and then it becomes complete and totally bounded, and therefore it is compact.
Okay, sir.
Okay,
And sir,
so now, yes.
sir, why this word relatively coming? Because we are taking closer in Y. So what's the relativeness?
No, this is, I mean, sometimes it is called pre-compact because it may not be compact, but its closure is compact, right? So, so relatively compact is again a word used for some set whose closure is compact. So this you can take as definition that just this means that TB closure is compact.
Okay.
Also, sir, like why we are taking Banach spaces?
Banach spaces is just to ensure that this thing is complete, right? So if I take this TB closer, it will be complete. I mean, one can talk about these things in just non-linear space, but uh, no, we will look at Banach space. In fact, later we will see a compact operator on Hilbert spaces only.
Okay, sir.
All right. So okay, let's define what is known as finite rank operator. So a finite rank operator from X to Y is a linear transformation from X to Y such that a linear transformation set T from X to Y such that the dimension of image of T, this is finite, right? So rank, you know, rank of a linear operator is the dimension of the image of T. So this is just saying that rank of T is finite. So it is called finite rank operator. And let us use notation also. So we will write B00XY. This is set of all bounded finite rank operators from X to Y. So note that the finite rank operator need not be bounded, because we have only defined that finite rank operator means that it is a linear transformation and the image space is finite dimensional. So we know that there exists unbounded, for example, if you take unbounded linear functional on a Banach space, then the image is just the a set of scalar which is one dimensional. So but it will be finite rank because the dimension is finite, right? So a finite rank operator, the way we have defined, it need not be bounded, but when we write this notation b0 xy, this is the a set of all bounded and finite rank operators. So we have this b00xy. This is a subset of b0 of xy, and b0xy is a subset of bxy. Right? So finite rank operator, bounded finite rank operator is compact, and a compact operator is a bounded operator. So why is this true? So we want to show that a bounded finite rank operator has to be compact. So if we take any bounded finite rank operator, so let T be a bounded finite rank operator, then we want to show that T is a compact operator. So if we take the image of this T, so this is finite dimensional. So this will imply that let's write this as Z. So Z equal to image of T. This is finite dimensional. So this will imply that if we look at the a closed unit ball of this Z, this will be finite dimensional. So therefore, this will be compact. So if we look at Z in Z, is that norm Z is less than equal to 1. This is compact. And then we want to prove that T of B is compact. So if B is the unit ball of X, then if we look at T of B, this is a subset of norm T times. Let us write maybe here instead of 1, if I write less than equal to norm T, then this is also compact because this is a closed and bounded subset, right? So This is a compact set. Let's write this as some k. So k equal to z in z such that norm z less than equal to norm t. This is compact. So now what we have is the T of B is a subset of this K. Since if we take any x in B, this implies norm of T of x is less than equal to norm T, and which implies that this T of x belongs to K. So therefore T of B is a subset of K. Now K is compact. So therefore K is compact. T of B closer is compact, because any closed subset of compact is compact. So this is a closed subset of this compact set, so it is compact. So this shows that any bounded finite rank operator is compact, and any compact operator is bounded. That is also true. Also, if we look at the identity operator, uh, the identity operator I from x to x. So when is this compact? Is this a compact operator? This is compact if and only if x is finite dimensional. Right? Why is this true? This is because we know that the unit ball is compact if and only if x is finite dimensional. So if you take any infinite dimensional Banach space, then the identity operator will not be compact. Okay, let us give one more example. So let x be equal to C01 with sup norm. Now let K from 0 1 cross 0 1 to R be continuous we can take R or C, whatever. So we have a continuous map. So now we can define the operator on X. So define T from X to X by T of any F. So this again will be, we want it to be a continuous function on this closed interval 0 1. So Tf of X we are defining as integral from 0 to 1 of K of xy times Fy dy. So we want to see whether this is a compact operator on X or not. So, okay, it is almost, it is time to stop now. So I'll just give a hint. So use the Arzela-Ascoli theorem to show that T is a compact operator. So you only have to show the that if you take the unit ball of X, then T of B, we have to show that its closure is compact. So if we show that T of B is equicontinuous and uniformly bounded, then by Arzela-Ascoli theorem, its closure will be compact, and that will imply that T is a compact operator. So you can try proving this using Arzela-Ascoli theorem. Otherwise, if there is difficulty, then I'll do that next in the next class tomorrow. So note that this week we have on Saturday also is Friday's schedule. So we'll have class tomorrow and on Saturday. Also, there is one announcement about quiz. So next week we will have one quiz, and the topic will be on Hilbert space. So I'll send the detail by email, the exact date, but you should be prepared for the quiz next week. Okay, I'll stop here.